All right, so let us begin. Hello and welcome everyone to week 6 of interactive live sessions for the course Computational Fluid Dynamics for Incompressible Flows. The course is being taught by Professor Amaresh Dalal from IIT Guwahati, and I'm Debjit I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some tutorial problems together. So, without further ado, let us get started. So, the topic of week 6 was hyperbolic equations and how to solve them using different computational tools. So, that brings us to question number 1 of today's session. So, uh, this is a match the following type of question. There are three uh, techniques which are used to discretize hyperbolic equations given in the left hand column, and on the right hand column are the different stabilities which those methods have. So on the left column we have Euler FTCS, which means forward in time and central in space. Then option B, we have Euler BTCS, which is backward in time and central in space. And option C is Lax method. And different stability conditions are given on the right hand side, on the right hand column, where we have option 1 unconditionally stable, option 2 conditionally stable, and option 3 unconditionally unstable. Now you'll have to match these columns with options on the each of the column with the correct one, and then find the correct answer. So we have question number 1 of today's session. It's a match the following type of question, as you can see, and we have two columns. One columns with different methods in which hyperbolic equations are discretized. So we have Euler FTCS, Euler BTCS, and Lax method on the left hand column, and their stability conditions in the right hand column. So we have option 1 unconditionally stable, conditionally stable, and unconditionally unstable. So you have to match each method with its proper stability. FTCS means forward in time and central in space, and BTCS means backward in time and central in space. And we have different combinations in the options given below. So option A is A2, B1, C3. Option B is A3, B1, C2. And option C is A1, B3, C2. And option D is A3, B2, and C1. So once you have figured out the correct solution, you can select it, type your answer in the chat box, or you can unmute yourself and answer. So if we take a look at the solution is option B, A3, B1, C2. So Euler's FTCS scheme. If we look at this, so our model equation was this: dou phi dou t is equal to some minus c dou phi dou x. In Euler's FTCS scheme, it is discretized as, you know, pi n plus 1 minus pin divided by delta t, and on this side we have minus c, then 2 delta x, and we take central difference over here, so I plus 1 minus I minus 1, and both at the time level n, because we are taking a forward in time formulation. So this is an explicit scheme which is uh, unconditionally unstable. This does not give proper results. Uh, so the solution becomes unstable. The error does not go down, it actually blows up. That's what von Neumann stability analysis tells us. Then if we go to BTCS, okay, to keep in mind that the C is greater than 0. That's the assumption that we deal in over here. So then we go to BTCS scheme, which is an implicit scheme in this scheme we discretize in a similar way. So we have n plus 1 minus phi I n divided by delta t, but on the right hand side, this time we have a similar central difference, but the points will be taken at the n plus 1th time level. So this leads to an implicit scheme, and this actually boils down to uh, a TDMA, a tridiagonal matrix, which can be solved using TDMA. And this method is actually unconditionally stable. So no matter what values of delta t, delta x you pick, the solution will remain stable. Then we have lax method, which is basically an modification of this FTCS scheme. So here we, instead of phi in, we take the average of phi I plus 1 and phi I minus 1. Sorry. And the rest of it remains the same. So we have delta c to delta x, then phi I plus 1 minus phi I minus 1, all at the nth level. And this method is actually turns out to be conditionally stable, with the condition being uh, this c delta t over delta x being less than equal to 1. This is also known as lambda, and this is the Courant number. Okay, so moving on, we'll move on to question number 2 of today's session. So question number 2 is asking us that for lax method, for CIR method, as well as midpoint leapfrog method, what is the condition for stability according to von Neumann stability analysis? Is it lambda greater than 0, greater than or equal to 0? Is it lambda less than or equal to 0? Is it lambda greater than equal to 1? Or is it lambda less than equal to 1? Now, lambda here is the Courant number. And it is given by some phi, okay, not phi, c rather, the wave velocity in a hyperbolic wave equation into delta t divided by delta x. So which of these criteria uh, is required for stability according to von Neumann stability analysis? For different methods, this applies to a multiple number of methods. Some of them are listed here. For lax method, CIR method, as well as midpoint leapfrog method. By the way, CIR method is Courant Isaacson Rees method. So if we look at the solution, it is lambda less than equal to 1. So basically the C delta t over delta x, this has to be less than equal to 1. This is known as CFL criteria as well, and it's seen in different schemes. So CFL criteria is Courant, Frederick, Levy criteria. So basically, there is a physical meaning behind this. That why does it have to be less than 1? So let's say we have two grid points like this, separated by a distance delta x, and there is a wave speed c in, let's say, going from left to right in the positive x direction. So in time delta t, if there is any particle, let's say at this point, any fluid particle, so in delta t it would cover a distance of c into delta t. So this distance covered by that fluid particle, if it is less than this delta x, then it is actually captured. So in going from this point to this point, this movement is resolved. Otherwise, if this is greater than delta x, then it would jump across, more than one point in one time step. So resolution of that becomes an issue, and as a result, if there are errors, that those errors tend to, exponentially grow with time. That's what von Neumann stability analysis tells us, that there is a exponential growth of error. Now let's say some alpha into delta t. Now if this alpha is greater than 0, so then with more subsequent time steps, this error would continue to grow. So this is some form of error is written in this way. And if alpha is less than 0, that actually decays with time and leads to a proper solution. So that's why this is how stability is defined, and you can uh, find out for different such methods like the ones discussed here and many other methods also. It ultimately boils down to this criteria: Courant number being less than equal to 1. Okay. So we will move on. We'll move on to question number 3 of today's session. Question number 3 says match the following schemes with their appropriate conditions. So there is Euler FTFS and Euler FTBS. Now these schemes are not appropriate for all conditions. They are appropriate for some specific conditions only. Those conditions are listed in the right hand column. So c less than 0 and c greater than 0. Here c is the wave speed in the wave velocity rather in the hyperbolic equation. So we follow our same model equation where dou phi dou t equal to minus c dou phi dou x. Here c is this c, wave velocity. Now, in which condition which scheme is appropriate? So Euler FTFS and Euler FTBS is appropriate for which situations? If wave velocity is less than 0 or wave velocity is greater than 0. So this basically means what is the direction of flow, whether from left to right or from right to left. And we have only two options. So we have A2 B1 and A1 B2, meaning FTFS is suitable for C less than 0 and FTBS being suitable for C greater than 0 is option B, and the other way around is option A. So let's have a look at the solution. Solution is option B, A1, B2, meaning FTFS is suitable for C less than 0 and FTBS is suitable for C less than 0. So it boils down to this: for C less than 0, we will discretize using Euler FTFS in this manner. So we have n plus 1 Cin divided by delta t. This would be equal to minus c over delta x. We will use forward difference in space. So plus 1 minus fi. I plus 1 phi I plus 1 minus phi I, and both of them at the nth time level. And for c greater than 0, we will use FTBS scheme. The left hand side remains the same. In the right hand side, now we will use backward in space discretization. So phi in minus phi I minus 1 n. And a combination of these techniques is basically the first order upwind scheme. So our choice of scheme would depend on the direction of velocity, and we will pick the upwind point for discretizing. So let's say if we have 3 points like this, We will take two cases, C less than 0 and C greater than 0. So if C less than 0, that means the wind is flowing in this direction. And let's say if we have I, we will pick an upwind point, which is I plus 1. So this corresponds to, so this thing corresponds to this. And if C greater than 0, that means the flow is from left to right. And with respect to the ith point, we will pick an upwind point, which is at I minus 1. So, and this corresponds to the second case, where we use FTBS scheme. Okay, so let's move on. Moving on to question number 4 of today's session. So here we have 4 options in the left hand column and 3 options in the right hand column. So first of all, there will be one option in the right hand column which is repeated. And what are these columns consisting of? So the left hand column consists of different methods and different schemes, and the right hand column consists of different orders of accuracy. So you have to match each method with its appropriate order of accuracy. On the left hand column, we have CIR method, which is the uh, current Isaacson-Rees method, as we discussed earlier. Option B, we have Lax method. Option C, we have midpoint leapfrog method. Option D, we have Lax-Wendorf method. And on the right hand side, we have different orders of accuracy. So the first option is first order in time, first order in space. Second one is first order in time, second order in space. The third option is second order in time as well as second order in space. So you have to match each method with its proper order of accuracy, and once you have done so, you'll have to pick the correct option from the correct combination from the options given below. The options are option A, A2, B1, C3, D2. Option B, A1, B2, C3, D3. Option C, we have A3, B3, A3, B2, C2 and D1. And option D, we have A1, B2, C2 and D3. So now let's have a look at the solution. The solution is option B, A1, B2, C3, D3. Let's try to solve this. So we have this current Isaacson-Rees method, which is first order in time as well, which is whose accuracy is first order in time and first order in space. The lax method is uses central difference scheme. Okay, so first of all, CIR method, this uses you know both FS as well as BS within it, which means forward in space and backward in space, and both of them are first order in space accurate. And it uses uh, FT scheme. So basically, let me write it down properly. So CIR method is actually a combination of FTFS as well as FTBS. So that results in, so if you're using forward in time, it would be first order in time. And if you're using either forward in space or backward in space, it would result in first order in space. So that is the order of this method. In lax method, what lax method does is it does a forward in time formulation but a central in space formulation. So this results in forward first order in time accuracy, and this central discretization in space offers it a second order in time, second order in space accuracy. So that is how the order of the accuracy is of lax method is first order in time and second order in space. And midpoint leapfrog method, so I'll write in short as MPLF. So this uses a central in time, central in space method. So as a result, it will have second order in time as well as second order in space accuracy. So that's how C3. And Lax-Wendorf method. This you can't directly do in this way. So this actually goes through a Taylor series expansion, and we replace all the spatial terms. So basically do phi do x as well as do 2 phi do x2 shows up, and we use central in space discretization for those, and finally we reach a form which is second order in time and second order in space accurate. So that results in A1, B2, C3 as well as D3, which is the correct combination given by option B. Okay, so we will move on. We will move on to question number 5 of today's session, which is asking us what is the main advantage of using a CIR method. Once again, let me write this down. CIR method is Courant, Isaacson, Rees method. So what is the main advantage of this method? Is it high accuracy? Is it fast convergence? Is it unconditionally stable? Or is it independent of direction of C? Okay, so let's have a look at the solution. The solution is option D, independent of direction of C. So how this CIR method works is we start with the original model equation for hyperbolic equations, which is dou phi dou t equal to minus C dou phi dou x. Now this is actually broken down into, say, okay, first of all, let me write it down this way. So I'll take both the terms on the left hand side and put right hand side equal to 0. Now there is a bit of algebraic trickery going on here. So what we will do is we will add and subtract mod x twice. So first of all, we will split the C into two, C by 2, C by 2. Then we will add as well as subtract mod of C by 2 with each term. And we have dou phi dou x as usual. Now what happens is if let's say C is greater than 0. So in that case, uh, this term goes to 0 and this term becomes C dou phi dou x, and okay, and this one, okay, there is one additional step before this. Let me write that down clearly. So we have dou phi, we discretize this dou phi dou t using a forward in time formulation, and for this particular term where we have C plus delta C by 2, this term we discretize using a um, so this term remains when C is less than 0, right? C is greater than 0, and in that case we will use a backward in time formulation, a backward in space formulation. So we have I minus 1 both at the nth time level, and here we will use forward in time, forward in space formulation. So we will have I plus 1 minus p at I divided by delta x both at time level n equal to 0. So okay, so here some funny things happen. If c is greater than 0, so that means delta c is positive, and this c plus c by 2 is equal to c. and C minus mod C by 2, this gives me 0, right? So this term vanishes, and we have this term vanishes, and this third term vanishes, and this term remains. So let me write this down clearly. So when C is greater than 0, this term, this remains, second term, and the third term vanishes. And all this actually leads to an FTBS scheme, which is proper for C greater than 0. Similarly, when C less than 0, this leads to, you know, C plus mod C. Here mod C now is positive and C itself is negative. So this becomes 0, and C minus mod C by 2, this becomes equal to C. So this term remains and this term goes away. And this actually boils down to a FTFS scheme, which is appropriate for C less than 0, as we saw earlier. So as a result, this formulation does not depend on the actual value of C. You don't know prior knowledge. You don't have to have a prior knowledge of the direction of C while choosing your method. You can discretize the entire domain in this way, and you can have different directions of C in different points of the domain as well. The scheme is formulated in such a way that a proper FTBS or FTFS would be formulated at different points in an appropriate manner. And finally, we will get the correct solution. So this is the main advantage of the CIR method. Okay. So moving on, we'll move on to question number 6 of today's session, which is asking us what is the stability criteria for solving inviscid Burger's equation using a McCormack scheme. So first of all, inviscid Burger's equation, this is a nonlinear hyperbolic equation. This can be solved using the McCormack scheme, but however, it is conditionally stable. You have to pick out what is the condition. Is it option A, delta t by delta x into u less than equal to 1? Is it option B, delta t by delta x u max less than equal to 1? Is it option C, delta t by delta x into u min or u minimum less than equal to 1? Or is it option D, mod of delta t by delta x into u max should be less than equal to 1? So let us have a look at the solution. The solution is option D, that is mod of delta t by delta x into u max should be less than 1. Now this comes from the fact that the maximum velocity, whichever direction it is in, that multiplied by delta t over delta x should be less than 1. So this is the current number max, so to say, which should be less than equal to 1. Okay. We can derive this by using, by applying von Neumann stability analysis on the McCormack scheme for solving inviscid Burger's equation. Okay. Let's move on. We'll move on to question number 7 of today's session, which is asking us which of these is a multi-step method. Is it option A, midpoint leapfrog method? Is it option B, CIR method? Is it option C, Lax-Wendorf method? Or is it option D, McCormack method? Let's have a look at the solution. The solution is option D, McCormack method. So what we do in McCormack method is we take two steps. So going from n to n plus 1, we go through one n plus half step. And here what we do is, we let's say we have some value I comma n, we go to some provisional value first, which is a representation of the value at n plus 1, but not exactly that. Then we correct it using, going from n plus half to n, and sorry. Then in the second step, we go from n plus half to n, where instead of this n plus half, we use an average of the value at n plus the provisional value, which is a representation of that at n plus 1. So that's how in two steps we go from uh, the value at the nth time level to that at the n plus 1th time level. Sorry, I did not do this correctly. So we go from n plus half to n plus 1, and in this step we use this. And in two steps we can use BTCS once and FTCS once. In what order we do doesn't matter. We can do each, like going from, for the first step we can use BTCS, and in the second one we can use FTCS. Similarly, we can do in the other order. In the first step we can use FTCS, and then in the second one we can use BTCS. Both are applicable. So this is what McCormack method is. It's a multi-step method in which we use two steps, and these are how those two steps are executed. All right. So moving on, we will move on to question number 8 of today's session, which is asking us, lax method is a modification of which discretization scheme? Is it a modification of option A, FTCS, option B, FTFS, option B, FTBS, or is it option D, BTCS? Let's have a look at the solution. It is FTCS. So how lax method is done is, first we start off with FTCS. We have our same model equation, dou phi dou t equal to minus c dou phi dou x, and we do FTCS on it. So first we will take forward in time formulation. So n plus 1 and n over here divided by delta t equal to minus c, and central in space differentiation. So we will take phi I plus 1 minus phi I minus 1, both at the nth time level. This gives us FTCS scheme. Now what lax method does is, in lax method, this term is replaced by the average of these two. So at the ith point, I'll take average of its two neighbors. So that it boils down in this way. We'll take half, then I plus 1, I minus 1, both at the nth time level, divided by, okay, so I'll now send over this delta t to the right hand side, and we have c, so we'll define lambda as c delta t divided by delta x. So that way we will have minus lambda over here by 2, and we have phi I plus 1 n minus phi I minus 1 n, and if we simplify this further, it will give us this explicit scheme with only one unknown in this side, and so it will be for I plus 1, we will have half minus lambda, so 1 minus lambda by 2 into phi I plus 1 at n, and that will be plus and plus. So we'll have 1 plus lambda by 2 into phi I minus 1 n. Did I do this correctly? Let's check the math once. So there is this c fine minus half. This goes that side. It's plus half minus lambda by 2. So 1 minus lambda by 2. And this one we have, so minus minus plus, it goes that way, it becomes minus, so it's wrong. So this will be lambda, this is plus, and this will be minus when it comes this way. So lambda minus 1 by 2. I hope I'm doing this correctly. So this is minus, send it over that way. Oh, sorry, this is plus, right? So this is plus, so that way it becomes plus half and plus 1 by lambda. So 1 plus lambda by 2. Right. So Lax method is basically a modification of this FTCS scheme. Okay, let's move on. We'll move on to question number 9 of today's session, which is asking us Crank-Nicholson as well as Euler's BTCS scheme can be easily solved by which method? So after discretizing using Euler's VTCS scheme, we have to solve it using some method, right? So which solution technique would be the easiest one for Crank-Nicholson method? Is it uh, so sorry, let me reframe it this way. For Crank-Nicholson method as well as Euler's BTCS scheme, after discretizing, we can solve those equations very easily using one method, one solution technique. Is it option A, Gauss-Jacobi method? Is it option B, Gauss-Seidel method? Is it option C, LSOR method? Or is it option D, TDMA? Now let me write down the abbreviations for this. LSOR means line successive over relaxation method, and TDMA means tri diagonal matrix algorithm. This is also known as Thomas algorithm. So for Crank-Nicholson method as well as Euler's VTCS scheme, uh, which solution method or which solution algorithm can be used to solve it quickly and easily? Is it option A, Gauss-Jacobi method, option B, Gauss-Seidel method, option C, LSOR method, or option D, TDMA? So we have one response in favor of option B, that is Gauss-Seidel method. Let us have a look at the solution. The solution is actually TDMA. So, or the Thomas algorithm. So what happens in both Crank-Nicholson method as well as Euler's BTCS scheme, if we go back to the formulation, so there we will have, the three unknowns in each equation in terms of something else. Uh, so it would be different for the two different schemes, and we will have coefficients like alpha, beta, and gamma over here. And this would be the generic form of the discretized equation. So now, if I take all points and write them down, so let's say I'll take alpha 1, beta 1, and gamma 1 like this. So the equation would, so the matrix would look something like this, and there would be 0 all over, and this side we will have all the phi's. So from phi 1 to phi n we will have here all these at the n plus 1th time level. which are unknown. And on the right hand side, we will have some function in terms of phi i's at the nth time level. Now phi i's means it doesn't have to be phi I only, it can be I plus 1, I minus 1 and all that, but all of them would be known values at the nth time level. So right hand side would consist of all these at the nth time level. And so if we come back to the matrix, it would look something like this. So alpha 1, beta 1, gamma 1 goes like this way. Then we will have alpha 2, beta 2, gamma 2, and then zeros all over. Similarly, in the last column we will have zeros all over, and alpha n, beta n, gamma n as the last three items, and zeros all over. So this basically gives us this tri-diagonal matrix. So we have three diagonals. Okay, wait a second, I did not do this correctly. So let me write down the matrix correctly. Sorry. So we will have beta n and gamma n in the first column, and alpha n, beta n, gamma n in the second column, and zeros all over. That is fine. So we have this particular column, this particular diagonal below the main diagonal itself, as well as one diagonal above the main diagonal. So we have these three diagonals. So this basically lends us to a TDMA, or Thomas algorithm. In a previous lecture, Thomas algorithm was discussed, and in the interactive session also this was discussed. So I'll suggest you to go back to that and have a look at the details of the algorithm. The videos are uploaded in YouTube, so you can go back and have a look. We are not discussing it today right now. Okay, does that make things clear?
Okay, sir. Okay.
So we will move on to the last question of today's session, which is question 10, which is asking us the speed of propagation of disturbance in hyperbolic problems is what? Is it option A 0, option B finite, or option C infinite? Hyperbolic problems. So if we have a system which is governed by a hyperbolic partial differential equation and we disturb it, so at what speed does that disturbance propagate? Is it option A 0, option B finite, or option C infinite? So we have one response in favor of option C infinite. Let's have a look at the solution. The solution is actually option B finite. So the simple way to answer this is if we go back to the model equation once again. So this is the model equation where the C was the wave speed, and this itself is the speed of propagation of any disturbance in a system which is governed by a hyperbolic PDE. And a more detailed way to answer this would be like this. So if we have a look at a wave, let's say something like this. This is x, and let's say at time t equal to 0, I have a wave like this. This is a disturbance as well, so this is at t equal to 0. Now this has a speed of c in this direction. Let's say it's a positive speed. So at some t equal to delta t, this wave would have propagated by this much. And mind you, this distance, this is given by c into delta t. And this curve I am drawing at t equal to delta t. Similarly, at a later time, it would have moved like this at t equal to, let's say, 2 delta t. And here again, if you take the distance between the two peaks, that distance would be c into delta t. So as you can see, this curve is actually moving with a finite velocity, which is c. Now, this is in contrast to uh, elliptic problems, in which the speed of propagation of disturbances are infinite. So how does that work? So let's say I have a domain like this. This is a solid, and I put different uh, values of temperature at the different walls. So in the left wall, I have T equal to TL. On the right wall, I have T equal to TR. On the upper wall, I have T equal to TU. And on the bottom wall, I have, let's say, some T equal to TL. And I'll have some temperature profiles like this. These are temperature contours. So contours are basically lines of equal temperature. So these are isotherms, we can say. Now, if let's say I take any of the four walls and change it. So let's say I took the left wall and I made this T equal to TL by 2. I halved the value of temperature there. So the temperature in the entire domain would immediately change and give some different contours like this. They won't cross. I'm sorry. Some different contours like this, and that change would be infinite. Sorry, that change would be instantaneous. So it won't take any time at all. Like as soon as I change the temperature at the left wall, the temperature within the entire domain changes instantly. So what does that mean? The disturbance which I caused has traveled to all locations instantaneously. So uh, the limit delta t actually tends to 0 over there. So the within a snap of a finger, the uh, disturbance spread over the entire domain, which is of some finite length. So some finite length divided by 0 time means what? Infinite speed, right? Does that make sense clear? So in elliptic systems, the speed of propagations of disturbances are infinite, whereas in parabolic as well as hyperbolic systems, these are finite. Okay, does that make things clear?
Yes, yes.
Okay. Do you have any questions on anything like today's session or something earlier in any lecture or any the assignment problems which are given in the course? You're free to ask any doubt or anything you have.
Actually, sir, our office is finished and reaching at home.
Okay.
It is difficult for us to join the session at 6
Okay.
p.m.
No, it's
If
not
it's
a
possible,
problem.
then you can shift from 6 to 7 p.m. start time of this online session. It's help us.
Okay, I'll try to talk to NPTEL and let's see if I can do that. But I can't give any assurance. Like it is not in my hand. Okay.
Okay, sir. Okay. And because just arriving at home, we didn't
No, no,
prepare
I
anything.
understand that.
Actually,
It's okay.
that's why we are not able to ask some question
Okay.
on these topics.
Okay.
Actually, I don't have today any.
Sure.
Next time, definitely I come with our doubt and
Good.
some preparation.
Okay, absolutely. So I'm here to, try to help as much as I can. And I understand that your daily lives can be constraints to attending these sessions. So that's why all these sessions are actually recorded and uploaded in YouTube. You can always go back and have a look at them at any time of your convenience. Okay.
Okay, sir. Okay.
Do you have the link to the YouTube channel? I can share it with you right now.
Sir, one more time, if you share, it's helpful for me.
Okay, okay, some other time then. And I guess in the NPTEL course page also, it should be shared over there. You can also
Yes,
have a look.
yes, sir. Yes, sir.
Okay. So let's end today's session. Thank you for joining.
Thank you, sir.
Okay. Okay.
Bye.
Okay. I'll try to look into that, timing issue. Okay.
Okay, sir.
Okay.
Thank
Bye.
you.
See you next week.